Here, we are going to start with a pair of simple linear equations, and we are going to look at their geometric interpretation and the geometric interpretation of their solution. So here is the coordinate frame on which we'll be plotting all the geometry. So let's get started with our first equation. Let's call it, say, equation A, which is 3x minus y equal to 7. Now we know that equations of this kind, ax plus by plus c is equal to 0, represent a straight line. In fact, that's the main reason why they are called as linear equations in the first place. So let's plot the line that represents this equation geometrically, and we can verify this even. Say this is a point on the line which is 4, comma 5. Let's substitute that here. 4 times 3 is 12, minus 5 gives us 7. So this point on the line satisfies the equation. Let's take another point. Say here is a nice point here. Say that is 2, comma minus 1. So let's substitute that. 3 times 2 is 6. Minus of minus 1 adds it. So 6 plus 1 gives us 7. So 2 points on this line satisfy the equation, and therefore the entire line satisfies or represents this equation. Let's do that for the second equation as well. The second equation is a little simpler. X plus y equal to 5. And here is a straight line that represents it. One can verify this. It is 5, comma 0. X and y get added to 5. And 0, comma 5 over here. So again, 0 plus 5 giving us 5. Okay. So this is the second line. And how about the solution? Well, we can do it algebraically here. We know the methods, elimination, substitution, or we can do it geometrically here as the intersection of these two lines. So here is a solution in a geometric way, and here is a solution found in a algebraic manner. Well, now there is one more way of representing this system of equations, and that is like a matrix equation given here. The coefficients 3 and minus 1 have become the row of this matrix, 3 and minus 1, while 1 and 1, the coefficients of the second equation, have become the second row. The right hand side, 7, 5, has become the right hand side of the matrix equation, 7 and 5. Okay? So this is a concise way of writing the same system of equations. What we have done here, we have taken the first row of this equation and represented it as a line. Then we have taken the second row of this equation and we have represented that as a line. So this point of view, or this way of representing and solving this system of equations, is called the row view. Okay, we are taking one row at a time, plotting them as geometric entities and solving it. But there is one more way of solving this system of equations, and that is the column view. So let's take a look at that. So instead of writing this matrix equation this way, we are going to write it in a slightly different manner. So I have written the first column here, 3, 1. The second column, minus 1, 1 is written here. And the right hand side, 7, 5, as before, is written here. And this equation we have written as x times this column plus y times the second column is giving us the column on the right hand side. So this column view also has a geometric interpretation. Let's take a look at that interpretation now. For that, we are going to take a coordinate frame again, and then we'll be representing these columns, which are also called as vectors. And that is for good reason. A column can be represented geometrically as a vector. And here is our first column represented as vector. The column is 3, 1. So we are going 3 units in this direction and 1 unit in the y direction, giving us this vector. Similarly, the second column can be plotted as a vector, minus 1, 1. So we'll be going minus 1 in the x direction and 1 unit in the y direction, giving us the second vector. Okay, the second column is this vector. And then we'll represent the third one, 7, 5. So we'll be going 7 this way and 5 in the y direction, giving us this point. So that is our vector on the right hand side. And then what this equation is saying is we have to take these vectors, the first vector and the second vector, or the first and second column, and mix them in the right amount. So we have to take x times or x quantity of the first vector, add to it, mix with it the y quantity or y times the second vector, and that should give us the vector on the right side. So we have to find these right quantities x and y. When we mix these vectors in that amount, we are going to get the right hand side. So to do that, we'll first look at the nature of this vector. See what this vector is doing. It is taking us in this direction, along this line kind of. Okay. So if we take negative times that vector, it can take us back here as well. Okay. Similarly, this vector is essentially allowing us to move along a direction like that. So we are going to think in terms of this direction. If we want to get this vector, how long or how far we need to go in this direction and how far we need to go in this direction. For that, we are going to draw a line from this point that is parallel to this vector. So we are going to take a kind of the locus or the direction parallel to this. Similarly, we'll be taking another line that is parallel to this vector. So now we have a path. If we want to reach this vector, taking only the help of vector 1 and vector 2, then first we'll be moving along this direction, taking help of the first vector. Of course, we'll have to stretch the vector, scale the vector, or take multiple copies of this vector and hop. Okay. Something like this. So if we take 1, 2, 3 copies of the first vector, that will allow us to reach this point. And from this point, what do? We move in this direction, which happens to be the direction of the second vector here. Again, we take this vector and sort of measure this distance in terms of that, and that reveals we need 2 times the second vector. So here is the recipe now. Okay? If you want to go from here to there, in other words, if you want to cook this vector, what you need to do? You need to take 1, 2, 3 times the first vector and add to that 2 times the second vector. And that gives us, that reveals the values of x and y. X is 3 and y is 2. So here is one more way of solving the same system of equations, but instead of straight lines, we are thinking in terms of vectors. Instead of rows, we are going to take columns. And indeed, therefore, this is called as the column view of this system of equations. One can do this in 3-dimensional space as well, and that is what we will do in the next video.